Okay, now let's introduce lemma 1. This is the linear combination lemma, and it's pretty straightforward why it's called the linear combination lemma. It says a linear combination of linear combinations is itself a linear combination. So let's prove this. So let's take linear combinations, right? So let's take a system. Okay, so let's do the proof here. Okay, pardon me. Okay, so let's look at a given set. Okay, so let's give a set. So we have C, let's do C sub 1, 1. So these are going to be C sub 1, 1. Oops. C sub 1, 1, x1, okay, plus C sub 1, 2, x2 plus dot 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 plus C sub 1 n x sub n, right? All the way through C sub m1 x1 plus C sub m comma 2 x2 plus dot 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 plus C sub mn x sub n. So we've got this matrix, or the system of equations, right? Or not system of equations, but a system of linear combinations. And so, what if we take all of these linear combinations and we construct and we combine those in another linear combination, right? So we take a linear combination of all of these, right? So now the C's, all the coefficients are scalars, and let's say we combine these linear combinations in another linear combination like as such. So we'll say D1 times C11 x sub 1. So again, these are linear combinations in X, right? So C11 x1 plus C12 x2 plus dot 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 plus C1n x sub n plus dot 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 plus, we'll call this d sub m, because we have m of these, so we'll call it d sub m. So d sub m times c m1 x sub 1 plus dot 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 plus c sub m n x sub n. Sorry about my writing. Okay. So all we did was we took the m linear combinations and we created a linear combination of those. So, and D is also a scalar. That's a scalar as well. So now what we're going to do is we're going to use the property of commutativity and move things around and regrouping and whatnot. And so we could do that since D and C are scalars. And what we get is we get this. We'll get, so x1 and x1, so we'll get d1 c11, how do I want to do this? Yeah, because we're going to have x1 here. So there's going to be an x1. So we're going to combine all the like terms with the x1s and then group all of the scalars together. So our coefficient is going to look like this. So I'm going to have d1 times c11 plus plus d2 times C21, right? Because that's going to be the next one. Plus dot 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 plus dm times cm1. Right? And then that's all going to be multiplied by x1. And then similarly, we could do that with each term, right? We could take the d2s and we'll group them up. And then all the way to the last one, which will be plus dot 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 plus, and then what do we have? We'll have dm. Well, hold on a second. Yeah, so it'll be d1 times c1n plus d2 times c2n plus dot 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 plus dm times cmn, and then all that will be grouped and multiplied by x sub n. Okay, sorry for my handwriting. And so now what we just have is we've just created and demonstrated that this is also, you can see, this is also a linear combination in the x's, which proves the lemma. And that's the end of the proof. Okay? So a linear combination of linear combinations is also a linear combination.